Hello, everybody. So then in this particular video, I'm going to go over some new eigenvalue facts. And we're going to use them at the very end to answer a question that pretty much started the whole eigenvalue, eigenvector problem off with. So first, we need a theorem that connects this to the big old, the following are equivalence theorem, the fundamental theorem of invertible matrices. So it winds up being, though, that if you have a square matrix, it's invertible if and only if the zero is not an eigenvalue. And it's incredibly easy to see why, because what if it was? So then if zero is an eigenvalue of A, then A times X equals 0 times X is equal to the zero vector has at least one non-trivial solution. And then after that, it's immediate, because if that has a non-trivial solution, then by the big, gigantic following equivalence statement, we have the fundamental theorem of invertible matrices. We know that one of them is that if the homogeneous equation has a non-trivial solution, then the matrix is not invertible. So therefore, if it is invertible, then zero cannot be an eigenvalue. And this argument can be easily reversed. So that's that. That's a statement that connects the idea of eigenvalues, with everything else we've done. After that, though, there's some other facts we need. This particular theorem feels like it's just there for manipulation, just to get you used to eigenvalues, but it's of numerical importance, because computing eigenvalues, by the way I've shown you, is ridiculous. No one does it this way. It's crazy. The reason is that the determinant, computing a determinant, increases at the speed of n factorial in terms of the number of computations for an n by n matrix. Now, sure, if it's just a 2 by 2 or a 3 by 3, that's not a very big number. But once you get to 5 by 5, 10 by 10s, 100 by 100s, or in real commercial use, 1,000 by 1,000 matrices, yeah, you never want to do this. It's nuts. It's crazy. Determinants, at least the way I've presented it, is of historical and theoretical use. It's there to help us explain why other things actually happen. But nobody actually uses them. No one actually uses them in real life. It's nuts. So we need numerical computational formulas that will allow us to approximate eigenvalues. That's why this theorem is here. You'll see later on in about a day, another class, I'll come back to the same idea. So I'll quickly explain them. If you have a matrix, A, square matrix, that has an eigenvalue lambda and a corresponding eigenvector x, that means then that instantly that lambda to the nth power is actually an eigenvalue of the matrix A to the same power. And the eigenvector is exactly the same. Lambda plus k winds up being an eigenvector of an eigenvalue of A times k times I, and it has the exact same eigenvector. If A is invertible, then A inverse has an eigenvalue, which is 1 over lambda, and it has the exact same eigenvector. Why these are all true is incredibly easy. Incredibly easy. I'll just show the third one. The rest, the first one's done in the book using induction, and the second one is part homework or something like it. So I'll really quickly show you. So then, for example, if you know that A is invertible, you now know that lambda, whatever it is, it's not 0. So then, since A is invertible, we know that we start off with an eigenvalue eigenvector pair. But we know A is invertible. That means if you take the A inverse of both sides, you would have x is equal to A inverse of lambda times x. But remember, with matrix multiplication, scalars can be put anywhere. And we know that since A is invertible, that the eigenvalue is not 0. So I can divide both sides by it. That then gives me that A inverse of x is equal to 1 over lambda times x. So then A inverse has an eigenvalue. It's 1 over lambda, and it has the exact same eigenvector, which is just x. And that's what number 3 said. So the important here one for us, though, is going to be the first one, that if you have a matrix and you take it to an nth power, the eigenvalues are all just taken to the same power. You don't get different eigenvalues. They're essentially the same, but taken to a power, the power corresponding to the power on A. So that means you get this really neat result. Suppose you have a bunch of eigenvectors. They don't have to be a basis to the whole space. It's just a bunch of eigenvectors with corresponding eigenvalues, lambda 1, lambda 2, and so on. And they don't even have to be different eigenvalues. They can be the same if you want. I don't care. So then if X is some linear combination of these eigenvectors, then if you ever want to take A to the kth power and then multiply it to vector X, taking the kth power of a matrix, that's no fun at all. That could be really awful. But it winds up being that it's incredibly easy if X can be expressed as a linear combination of eigenvectors. Because what you wind up doing, if you take A to the K times X, that is A to the K times C sub 1 V sub 1 up to C sub R V sub R. But by matrix multiplication, you just distribute that through. That would then give you C1 times A to the K times V1 plus all the way down to plus C sub R A sub K V sub R. But from what I just showed you, if you were to take a power of the matrix times an eigenvector, the result is actually just the eigenvalue to that exact same power times the exact same eigenvector. And that's true all the way down to C sub R. You have a power of A multiplied to an eigenvector. The result then is just the corresponding eigenvalue raised to the same power multiplied to that eigenvector. And that's it. It's neat, right? It means that taking powers of matrices is actually not that bad at all. It's incredibly straightforward, provided that the vector can be easily written as a linear combination of eigenvectors. Now you have that. You now have a reason why we want to talk about the next portion of the course, at least the next videos I'm going to start with. When can we say that we have an eigenbasis? When can we say that for a certain space that we have a basis where they're all eigenvectors? Because if that's so, then we can always write every vector in the space as a linear combination of eigenvectors. And that means taking high powers of a matrix times that vector is incredibly easy to do. You need a reason. You need like a application to justify why we want to do this. So remember this? We had that toothpaste problem where the matrix was a matrix of percentages where every column added up to 1. And they correspond to the percent chance that someone stayed with brand A or they went to brand B, or they stayed with brand B or they went to brand A. The overall thing we wanted to know is that in the end, what percentage of people will prefer brand A, what percentage of people will prefer brand B. And we found out that we had to do this particular high power matrix, multiply it to our initial population percentages, and see what happens in the limit. Well, we can now find out the real answer without hand waving at all. I can give you exactly why it's true. So to do so, there's a sneaky thing. Look at the matrix. Let's find out its eigenvalues and eigenvectors. So I need to know its eigenvalues. So let's find the characteristic polynomial. I'll set it equals 0 to get the characteristic equation. I'll solve that to get the eigenvalues. The eigenvalues here are 1/2 and 1. For each of these, we have an eigenspace. Let's find each. So for E1, that's the null space of A minus 1 times I. So I just wrote down the corresponding matrix of A minus I. I row reduced it, and from that, I found the basis for the corresponding null space. A basis that would work would be 0.4 and 0.6. Notice I made sure the vector here is a vector of percentages so that they overall add up to 1. I could have used any multiple. I could use any multiple of that particular vector. It just chose that one because I know that I want to get percentages in the end. Notice that the algebraic multiplicity of this eigenvalue is 1. Its geometric multiplicity is 1. The geometric multiplicity is less than or equal to the algebraic multiplicity. Now we'll do the same thing for the eigenvalue of 1/2. I need to find out what is E sub 1/2. That's the null space of A minus 1/2 times I. So I want to find a basis for that null space. So I have the matrix. I take A minus 1/2 times I. That gives me the matrix that you see here. 0.2, 0.2, 0.3, 0.3, and then I row reduce it to get the reduced row echelon form of 1, 1, 0, 0. From that, remembering that it's actually an augmented matrix with zeros on the right-hand side, I'm able to find a basis for that null space. And this time I chose to write the basis this way as 0.1, negative 0.1. And you might wonder why? Why? Because it makes it work out nicer. I could use any multiple of that vector. I could use any multiple of that vector. I'm choosing that multiple though for reasons. It'll just make things easier to understand in a second. So again, I could pick any multiple of that vector to be a basis for this particular eigenspace. I chose this vector for a reason, which you'll see in a minute. The important thing though is that the geometric multiplicity is 1. So there's only one vector in the basis. And the algebraic multiplicity is also 1 because lambda minus a half occurs only once in the factorization of our characteristic polynomial. So the power on it is 1. The algebraic multiplicity is 1 also. Notice that these two vectors, the vector in the first eigenspace that creates a basis for that space, and the eigenvector in the second eigenspace, which creates a basis for that space, those two vectors together are actually linearly independent. There's lots of reasons why. The obvious reason is these two vectors are not multiples of each other, so they are instantly independent. But there's a better reason that you're going to learn in a minute or two. So there's a better reason, but we're going to learn in a little bit. So let's just go with these two vectors are linearly independent. But since the dimension of R2 is 2, and these are two linearly independent vectors in that space, they form a basis of R2. So every vector can be written as a linear combination of these two. Let's just write the original percentages as a linear combination of those two vectors. You can now tell, by the way, why I wanted the second eigenvector to be 0.1, negative 0.1, because then the addition of the two eigenvectors is the percentages that I started with. Okay, so then I'm going to take this matrix. I'm going to take this vector 0.5, 0.5. I'm going to take it. I'm on pre-multiply it. That means multiply it on the left. Pre-multiply it by a to a power. And let's just see what happens. So a to a power of our starting percentages is a to a power multiplied to these eigenvectors. But you just learned how to do that. You replace it with the eigenvalue to the same power times just the eigenvector. So a to the n times the vector 0.5, 0.5 is this particular sum. Now notice what happens. What if we say n becomes ridiculously large? If n becomes ridiculously large, this part here is always just 1. It never changes. But if n becomes incredibly large, this is a half to a power, where the power is growing without bound. So this gets incredibly close and approaches 0. It gets as close to 0 as you wish. So in the linear combination, you get 1 times the first vector plus something really close to 0 times the second eigenvector. Obviously, this whole portion then just approaches the 0 vector. And the only thing we have left is that. So it seems then that if you take this matrix to a high power and multiply it by the pre-multiply on the left-hand side to the vector of initial percentages for our population of 50% and 50%, the population tends towards that 40% will prefer brand A in the end, and 60% will prefer brand B. And that's the real way to do it. So I've led up to this moment by looking at this problem multiple times. But this is the real way to do it, to explain what percentages will happen in the end. If you're ever wondering, when people say to you, well, they use analytics in order to solve that problem, or they use analytics on their baseball problem to figure out what should be done. This is it. That's it. This is the basics of it. It's all linear algebra. It's just linear algebra using improbabilities with statistics. It's all this stuff. This is the foundation of it. So then you're starting to get towards some cutting edge type mathematics now, at least of how it's used mathematically today in the last 40, 50 years. All right, I think that's enough for that video.